Okay, so welcome to another week of AA203. So starting from our usual roadmap, in the last week or so we have started, basically we finished the optimal optimal control part of the class, and we moved into the top half, which basically relates with learning-based methods for optimal control. Last week we focused a lot on, on Monday we focused on more classical methods to learning-based control. So we looked at things such as system identification and adaptive control. And then on last week, Wednesday, we started to introduce the general framework and terminology for imitation learning and reinforcement learning, and kind of starting to build a bit of a mental model about how to see different methods and different algorithms within these two subclasses. And so specifically today, we'll then zoom into the specifically imitation learning section of what we discussed on Wednesday. And so if you remember, we basically introduced imitation learning as basically an umbrella term that encompasses, broadly speaking, kind of two main classes of approaches. We started from behavior cloning as essentially a mechanism where we want to have access. So we always assume we have access to a data set of couples of states and controls, which we collected by observing some expert, kind of executing some demonstrations in the real world, for example. And then in behavior cloning, we want to use this data set to kind of directly learn a policy or approximate the policy that is being used by the expert. Concretely, the object that we wish to learn will be something along the lines of a policy pi of theta, for example, a parameterized policy with some parameters theta, that is essentially representing a distribution over controls given states. And we want to approximate this from the examples that we get in our demonstrations. We then also loosely introduce inverse reinforcement learning, whereby, in this case, the objective is to approximate the reward function or objective that is optimized, that we think it is being optimized under the hood by the expert himself. And specifically here, the object of learning will be to approximate or estimate a reward function R that is basically a measure that maps couples of states and controls to a scalar measure of success. And so for today, kind of coherent with this general roadmap, we'll be discussing behavior cloning first. We'll be introducing a number of common pitfalls, which we already slightly hinted to in our last lecture on Wednesday. And specifically, I would say, starting to look at traditional mechanism for which these pitfalls are being addressed. And then we'll have a brief mention on other paradigms that fall within the behavior cloning hat. And then we'll look at inverse reinforcement learning. So just to briefly recap in one slide, the lecture from Wednesday, we started by seeing behavior cloning essentially as supervised learning of behavior, right? So we introduced the general notation of supervised learning, whereby we essentially want to learn a parametric mapping that maps some inputs X to some outputs Y. Kind of prototypical example would be the classification problem, where we want to map some image representation, for example, an RGB image, an RGB that represents the image of a cat, to its label of the respective object or thing that is actually being represented in that image. And the way to do this is by taking a data set of pairs of this mapping that we want to estimate, and then learn it through some sort of loss minimization. In behavior cloning, we want to do something very similar to some extent, because we want to collect a data set of these expert demonstrations. And exactly as we would be doing in supervised learning, we'd want to train a policy that is this mapping that optimizes some metric of performance. And so we saw how kind of the general skeleton of behavior cloning algorithm, loosely speaking, really looks like something like take supervised learning and now apply it to trying to estimate behavior. So, but the question here is this really it, right? Does this work, or are we done? And in practice, as you can imagine, most of the times this is not it, in the sense that there are a number of common pitfalls and failure modes that could happen. And so today we'll basically be looking at strategies to address these failure modes. And I would say look at different techniques that kind of frontier approaches, specifically in learning-based control and robotics, are currently doing to make these techniques work. Okay, and so let us start from introducing the common pitfalls that could emerge. And the first one is the one of compounding errors. Specifically, we mentioned multiple times how in statistical learning theory, kind of a classical assumption that is made is that data is independent and identically distributed, or IID for short. Loosely speaking, this means that we are taking some distribution of P of X, which we wish to approximate. To do this, we only have access to samples or realizations of that distributions, x1 to x3 here on the slide. And we want to learn typically a parametric model that approximates this P of X that we care in learning. And we saw that, again, generally speaking, in statistical learning theory, we assume that the samples and realization that we observe are IID from the distribution that we care about. When trying to learn behaviors, however, kind of predictive controls influence the future state that we observe. And we loosely and briefly discussed this idea of the fact that since we are agents within our environment, there could be this problem and issue of compounding errors, whereby if our policy is making even very small errors, it could compound over time, that is, throughout the temporal kind of unrolling of our trajectory, which lead to making bigger and bigger errors over time. Slightly more formally, kind of theory here formalizes this problem as the fact that the state distribution induced by the expert policy and the state distribution induced by the learner, that is the policy that we wish to learn, essentially diverge and are not the same. And this is in theory referred to as the covariance shift problem. So to make the notation on the slide more concrete, when we say the state distribution are under the expert, that is P of expert of X, what we're essentially saying is, for example, the probability of the initial state times the product T that goes from 1 to T of the expert policy so the probability over the action induced by the expert policy given the state xt times the transition function of our environment. Right, so this is basically encodes the probability distribution of all the states that we could observe by following the policy or the distribution of our actions induced by the expert. Very similarly, kind of the state distribution under our policy, P of pi theta, would essentially be defined exactly the same, where here we just used the distribution over controls induced by the policy that we're currently learning. And I would definitely advise you to check out this reference here on the slide, because there is theory that basically shows that the probability of making mistakes under our policy essentially grows quadratically with the length of the trajectory. So here, assuming that there is a probability epsilon to make a mistake in our prediction from our policy, then the probability of making mistakes grows quadratically with the length t of our trajectory. Of course, here the error kind of assumes that we are working in a discrete world where we have to pick between one of n possible actions. And epsilon is the probability of making an error in that prediction. But there is a lot of theory that goes about formulating this covariance shift problem more theoretically. But I hope the intuition here is clear. Yes?
The states obviously aren't the trajectory, but the trajectory themselves aren't independent.
The trajectory themselves are independent, yes. This is a good question. So in general, for now, and I would say throughout the rest of this lecture, we're assuming that you're interested in learning the feedback policy. So there is a mapping from the instantaneous state xt to the instantaneous control ut. And our data set, therefore, is just a collection of tuples of this realization. Okay. And so this is for the compounding error problem. A second problem is the one that here I refer to as multimodal behavior. And specifically, in many tasks, there is this there is this characteristics whereby there could exist multiple and equivalent solutions to solving a control task, right? So take the pictorial example of flying a drone past a tree here on the slide. If we were to be human experts or human that are kind of joysticking this drone around, we would be in a situation where flying to the right or to the left of the tree would be equivalently good to some extent. And the problem here arises when we want to take this data set of collected demonstrations from, for example, human rollouts, and use these data sets to kind of compile or learn a policy that tries to approximate this behavior. Slightly more formally, the problem here is that we find ourselves in our situation whereby the policy that we wish to estimate is actually representing a multimodal distribution over controls given states. For example, like in this case, we might want our policy pi of theta to perfectly approximate this bimodal distribution over here. And the problem here emerges in the moment where we, for example, try to estimate things or kind of fit this distribution through pretty standard metrics, for example, mean squared error or minimization. And the point is that if we were to take, say, a neural network and try to fit our data through mean squared error minimization, we would be essentially learning a policy that tries to predict exactly the mean of our distributions, right? So what we're saying is that we are in a situation where we would like to approximate ground truth behavior distribution that looks something like this. That is my model. But if we were to use mean squared error as our loss for model for data fitting, our policy would then be incentivized to learn something that correctly predicts the mean of this multimodal distribution. And you see how in this case, this is actually probably the worst thing that we could do because it fits exactly in the middle because it tries to kind of balance out errors between both modes. And this is actually a problem that is extremely common in practice. For example, just consider where we are collecting data from multiple experts, which might behave differently in the same condition. And so this is something that we will have to take care of. Does this make sense? Any questions on this? Okay. And so for the rest of today, we will basically be building what I'm calling here a useful mental model for basically developing techniques that are remedies for these issues. Specifically, we'll be looking at algorithms, which basically try to address these problems specifically, or at least from an algorithmic standpoint. We'll be looking at ways in which we could address these problems from a data collection perspective. And then we'll be seeing how we can use expressive model classes to better represent the distribution of our data. And so specifically, the first two bullet points here on the slide, that is targeted algorithms and data collection, will be focusing on the compounding errors kind of issue, while the third one will focus on the multimodality of our policy in our data. Okay, so let us start from the first one. So algorithms that try to specifically devise methods to target these issues. And a very important aspect, which I want to highlight, is essentially the value that there is in corrective data. So until now, we're basically discussing a situation where we are collecting data from an expert, and we have always kind of hinted at this fact where we basically want to compile the performance of our expert into a learned model, a parametric function. And we always said that the performance of our model is at least at the kind of ideally as good as the quality in our data. And so kind of it probably came as a following thought, the fact that we want to keep our data kind of the best possible, right? So we want to collect demonstrations that are exceptionally good in solving the task. The problem is that if we do so, most likely we'll be ending up with a data set that is extremely narrow around a specific kind of behavior in solving that task. And if you wish, this leads to the kind of a counterintuitive fact. Because in general, if we want to apply behavior cloning to our learning-based control problem, there is a lot of value in leveraging examples of errors that have been taken by the expert and ways to recover from those errors. Because in practice, whenever we deploy our policies in the real world, the policy will be making some errors. And so if we have an extremely perfect data with no errors whatsoever, in those states where the policy actually makes errors, it will have no clue of how to recover from those errors. And so there is this paradox whereby learning from a broader set of trajectories that make some mistakes, but also shows ways to correct from these mistakes, is in general more valuable than learning from a narrow set of perfect demonstrations. And one way to automate this labeling and collection of corrective data is through an algorithm that is known as Dagger. And specifically, Dagger is a well-known method to address this covariate shift problem through what are called data aggregation techniques, which is also where the name comes from. And I think it's probably useful to go through a pseudocode of how at least the plain version of Dagger looks like, and then we discuss this a little bit more in detail. And specifically in Dagger, we start from an initial data set of expert demonstrations, things that we have collected by running some policy in the wild or observing some human. We'll have an initial policy, pi theta superscript 1, where here the superscript refers to the number of iterations of the Dagger algorithm. So Dagger will be an iterative algorithm where we are iterating from 1 to n iterations. And so here the superscript refers to the policy that is derived at iteration I. So indeed, so what Dagger does is we start our iterations. And for each of these iterations, we will be collecting some trajectories, tau, which basically represent the couples of states and controls, which we observe by letting the learner policy interact with our environment. So we have a given policy, we let it interact with the environment, and we collect data from these rollouts. What we want to do is then we want to take these states that we have visited during our rollouts, and in these states, we want to query our expert for relabeling. That is, we want to take those same states, xt, and for those states, we want to relabel the control that was originally taken from the learner with the control from the expert. Once this is done, we have a new version of our dataset, the superscript I, and we aggregate it with the original dataset which we had for learning. And so this is where the aggregation part comes from. We then take this aggregated dataset D and use this to train a new version of our policy. Right? So maybe slightly more visually, we are saying that we have a policy, pi theta 1, given to us. This could have been given to us by an offline dataset that we have and trained on this. We then have our environment, which might look like something where we want to go from some starting points to some goal points, where we are seeing examples of rollouts of our policy. And this leads to a data set of states and controls, where the controls are the ones that the learner executed. So we can then use this data set to basically relabel those controls with controls given by the expert. This creates a new data set, D superscript I, which we aggregated to the previous one and train on the updated data set. So why is this useful? The problem, the point here is that by doing so, we are directly querying the expert to relabel states exactly in those states where that are currently being visited by the learner itself, right? So we were talking about this discrepancy between the distribution of states induced by the learner and the one induced by the expert. In this case, we are explicitly querying the expert in those states that are that would be followed and are essentially drawn from the state distribution under the learner. Yes, I think, yeah.
Are you just relabeling there as a successful control and then relabeling it as an expert and retraining that as the expert, or training it from your original expert?
So here we are assuming we have access to an expert that we can query. This could be any policy that we think is good enough for us to be an expert. And we are using this to basically generate new labeled data for us in some way. Does it answer your question?
Yeah.
Yes.
In practice, if the source of the expert policy is a human, is this kind of like a discrete process where you would have to like step through? Because if you want the exact same states, you have to like step through and like not continuously provide input, but like go like state to state to state and provide a discrete input, and then that is the relabeling process.
It's a great question, because this is like, if you wish, like one version of this is like you would see Dagger V0, right? So this is the base version of Dagger. There is an extension to this, which is referred to as human-gated Dagger. Which will be in the next slide, where basically here we would be picking a specific point in our trajectory where we think maybe the learner made a mistake. And here we assume we have a human that basically intervenes and generates a new full kind of continuation of that trajectory. Concretely, kind of you have a robot arm that is doing some task. You're physically looking at the arm while it's doing things. But here you're seeing that maybe it's spilled over something, and so you're taking over, and from there you're maybe teleoperating the arm to generate the new trajectory.
And in that case, you wouldn't be limiting the augmented data set to have the exact same states as the original one. You'd allow yourself to like explore a different part after the mistake.
Mm-hmm. Yeah, which in a way, this is a nice segue, because if you think about it, this is only one iteration of the algorithm, but if you repeat this, then you will be having rollouts of a new policy, Pi2, which has a different state distribution, right? And so here you will be covering a new set of states. So kind of very high level, kind of Dagger is an automated way to take your given policy, you let it interact in your environment, and you basically expose failure modes in such things, right? You basically follow what the policy will be doing, and you correct those failure modes. Once you've done this, you might be maybe creating new failure modes, or you might be just observing new failure modes, and you keep iterating this process. Okay, and so essentially, kind of Dagger really operates as a form of iterative supervised learning, because we're using supervised learning as this inner learning component, but we're really creating this iterative scheme where we query the expert in order to relabel states that are visited under evolving versions of the policy itself. And if you think about it kind of at a high level, what we're saying here is that you can see Dagger as a data efficient way of querying the expert, because we're saying we want to use the expert as a mechanism to generate corrective behavior when the policy fails. And in this way, we are directly probing the expert exactly on those states that are visited by the policy where it fails, right? So here we are basically following the state distribution under the policy, seeing where it failed and relabeling, which is a pretty data efficient way of collecting these corrective behaviors. Kind of the other extreme would be that in order to collect all the corrective behaviors that you care about, you would have to run this maybe on kind of all the possible states that your policy would ever encounter and relabel everything, which is extremely expensive. So this is in a way pretty data efficient, but querying the expert depending on your scenario is in general something very expensive. So again, depending on the task, Dagger might or might not be something feasible. And so here we looked at the naive version of Dagger, but there are different ways that you can maybe modify the basic algorithm. One could be confidence-based methods, whereby here we are querying the expert on basically all the states that the policy visits during those rollouts. But we could maybe select some metric of uncertainty from the learner itself and only query the expert on those states where the learner was particularly uncertain about its answer. The other mechanism is also, as your colleague was referring to, is this human-gated dagger, where we have some humans that are kind of supervising the operation of our learner and directly intervening when there is a mistake. Yes?
So if you don't have human in the loop, is the benefit of this like trying to make like a lighter weight policy? Because you have an expert policy already, but you're not using it for some reason. So does this make something that like runs faster online?
For example, that would be one way. So I would say, in general, like if you kind of zoom out in all the methods that we're seeing in this class, I would say all of these are relevant, although definitely there is being a shift towards learning-based or more end-to-end architectures. The point is that kind of getting reliable data for these end-to-end architecture nowadays, I would say even in frontier models, typically relies on some more classical approach to generate labels for those. And so in some way, you could see this as a way of distilling some maybe extremely expensive, indirect method for optimal control into a fast neural network that can approximate it. Yeah. Okay. Any questions on Dagger before we move on? Okay. So we saw how Dagger is one example of an algorithm that directly tries to target these covariate shift issues. Let us look at how we could do this through data collection. And I want to do this through two case studies and going through two examples of this. So in this case, this was, I think, one of the early works from NVIDIA on autonomous driving. I think it dates back around 2016. What they basically tried to do is learn a neural network for basically deciding kind of the steering angle of the car while receiving as input some images coming from some cameras that were mounted on board the car. And let's see, yeah. So basically in this study, which again was now more or less 10 years ago, what you would see, they started from something which was clearly not working, also maybe being a little bit dangerous. But then the point of this work is that they started collecting more data for basically more demonstrations of humans driving cars and recording these tuples of images and steering angle decisions. And they, at the end, reached a performance that was, to some extent, impressive, especially at the time, and showed some pretty consistent behavior. The point is that, of course, this was pretty exciting at the time. Nowadays, we have made clearly some leaps from this. But one thing that I want to highlight from this work is something that you will observe if you read through that paper and look at the specific framework and architecture that they designed. Specifically, again, as we were saying, the overall problem was taking some camera images. Here they had three, kind of a center, a left, and a right camera. They have some recorded steering wheel angles from human drivers. And the overall goal was to learn a convolutional neural network to basically learn to approximate and predict those steering wheel angles from the images. Here I'm glossing over this box because this is exactly the, I think, interesting part from data collection technique, and specifically data augmentation technique. So again, kind of pictorially, this is the kind of situation we are in. We have a car, we have our three cameras, and we have one recording of a steering wheel angle, right? So the one that the human actually executed. However, if we think about it a little bit more closely, the two side cameras could be used as an example of the car slightly drifting off the center of the lane. And we could use these observations to fictitiously augment the data set with some steering angles that are actually seeing this camera image and then correcting from this camera image to kind of recenter itself in the middle of the lane. Right? So in general, correcting data set of driving mistakes is something that is very dangerous and expensive. You don't want to be collecting on purpose corrective data where you're driving off the road and then going back again on the road. And so in this work, they actually came up with this pretty neat trick whereby they are augmenting the data they collect from human drivers to fictitiously generate these corrective data by taking the side cameras as if they were front cameras and manually adjusting the steering angle for that camera. And so this is, I think, an example of how you could try to embed this corrective behavior, not from a perspective of the algorithm, but from the perspective of data collection and augmentation. A very similar idea was also presented in this work from the University of Zurich, where here the goal was controlling some quadrotors to indeed navigate some hiking trails, I think in the Swiss Alps or mountains, from camera images. The setting is very similar to some extent. We have some image camera, specifically a front camera view, and we want to output, this time, a discrete distribution over actions. That is, go straight, turn left, turn right. And once again, very similarly, what you see in this work is something that really resembles the previous work from NVIDIA, where here you had the researchers actually wearing this fancy headband with, I think, 3 GoPros mounted on it, and collecting data by literally walking over hiking trails, and specifically labeling the actions according to those same augmentations, right? So here for the frontal camera, they were labeling it as a go straight action. For the left one, they were labeling it as a turn right. And on the right one, they were labeling as a turn left action. Indeed, here's the fancy headlamp. And so you would see that this kind of works in practice. And so they got something that was, at the time, pretty reliable in navigating those hiking trails. Okay, and so here we saw 2 examples, but I think the main message that I'm trying to bring along is this idea that we, in trying to address covariate shift from a data perspective, we want to be intentional with data collection, right? And specifically, we want to intentionally add mistakes and correction for those mistakes in our data. So this could be as in these examples where we want to add some fake demonstration of corrections, this example of the side cameras. Or from an algorithmic perspective, we want to use algorithms that automate the collection of this corrective data, as in Dagger. Yes?
On the prior example of the drones, it made me wonder, when you're collecting this data and training whatever model is being used, is it possible or realistic to train, like in the case of the drone moving, train it based on the decisions that are being made, like this is why you go left and not like in the tree, while also having it not be reliant on the dynamics that are inherent to the trained data. Like the way that a human moves with something on their head, like just flopping it down, and you can't suddenly fly up 2 feet higher than you are. Which, for a drone, that might be advantageous for the tree or something. They can take advantage of things that you can't do. But if they're trained on the data that comes from something that's constrained to like human dynamics, is there a way to detach the behavior or control of the drone from the dynamics that are sort of built into the data that's trained on?
I would say not from the perspective of imitation learning. So in imitation learning, we are, again, at face value, we are trying to approximate and imitate the behavior of some expert. And that's about it. So we don't really want to go beyond what the expert is able to do. And we typically won't have access to data that is beyond what the expert is able to experience. So in general, I would say no. This will probably be something that will be extremely relevant from the perspective of reinforcement learning, where there we are not trying to approximate some behavior that is being shown to us by some expert, but we want to interact with that environment, maybe a simulator of the real world, and experiment with different strategies. Yeah, yeah. Okay, and so we covered it. We covered algorithms. We covered data collection. Let us look at using expressive models to address or partially solve the issue that comes with multimodal behavior. And specifically, we'll be looking at two main classes of methods. The first one will be including history of observations. We'll see slightly, we'll see shortly in the next slide, or using expressive function classes to better approximate and capture the multimodality in our data. So a brief mention on using history of observations is that until now, and whenever we framed the MDP problem theoretically, we always assumed that the state is a perfect representation and that capturing all previous history in our system. In reality, especially if we are working with images, we won't be dealing with the ground truth full state representation of our system, but we will most likely be dealing with observations of that system, right? Which are only partial informations or partial observations of the actual system. And so in this case, there is benefit, sometimes, depending on the applications, on rather than defining a policy as a distribution over actions given the instantaneous observation, xt, in adding a sequence of past observations to our context, essentially. In the case of behavior cloning, this is particularly relevant in the case where we're maybe collecting data of these tuples, states, controls, from humans' demonstrations. Because if you think about it, here, if we try to learn this policy from data, we are basically assuming that the human that has been collecting data for us, given the same observation, will always behave in the same way. Right? On the other hand, history could be an interesting confounding factor to basically add to our context to differentiate between different observations. Again, let's make a concrete example. Say that our X for us is just the front camera of our car, and U is our steering angle. Then if X is only one snapshot of the current history, we basically have no idea of maybe the speed of our car or any other relevant measure of that could be useful for decision making. And we are implicitly assuming that given the same kind of front car camera image, we would be always behaving in the same way. On the other hand, if we assume to have a history of previous camera images, then we might be capturing more useful information for decision making. In practice, this is typically handled through basically your favorite sequence model, where it could be transformers, could be recurrent neural nets, or something of the sort, where the policy then basically becomes something that takes a sequence of states or observations and outputs the next action. So again, pretty high-level discussion, but I think it's worth mentioning. In practice, I would say also my experience with including history in defining the behavior policies is usually very empirical. So you will be doing some sort of ablation where you're maybe trying out training your policy on your same data set with varying number of history time steps in the past and seeing what works best. Okay, but let us move to, I think, something that is more fundamental, which is this issue of wanting to capture the full data distribution. Right? So we made before this example of the drone flying past the tree, and we could have these two equivalent solution modes or behavior modes for our policy. And so the goal for us, rather than fitting this mean value of this potentially multimodal distribution, what we want to do is represent the entire distribution. And to do so, let us briefly revisit what it actually means for us to parameterize or devise a parametric function to express full distributions. And this will loosely depend on whether the distribution that we want to output is discrete. So something like a categorical distribution over a finite set of possible actions, say the 4 cardinal directions, moving up, down, left, or right. Or if this is continuous, it could be something like capturing the mean and the standard deviation of what our desired steering angle is. In practice, how we do this is we would say that we wish to define a neural network that outputs these parameters of our distributions. We could either have a neural net output the logits or the individual probabilities for each of our discrete actions, or we could have a neural net that basically represents the mean and standard deviation of a candidate Gaussian over kind of possible steering angle commands. The benefit of the discrete distribution is that it naturally handles multimodality, right? So say that, again, this is the distribution that we wish to have our model output. If we discretize this naturally continuous state into bins, and then assign a probability to each of those bins that sums up to 1, we might be very well able to capture this multimodality by learning something of this sort. Right? So discretized representations are actually very powerful because it's something we can do very well. So we could just learn this through cross-entropy, which is pretty standard in supervised learning, and get out of this something that naturally represents multimodal distributions. At the same time, I think pretty obvious downside is that depending on the dimensionality of our output and the discretization that we're interested in, and that is maybe relevant for our application, we could have a lot of bins a lot of probability kind of logits to estimate. And so this scales poorly with the dimensionality of our action space in this case. The pro of using kind of a continuous distribution as our output representation is obviously that this naturally captures the continuous nature of our actions, so no discretization required. But this might not be very expressive, right? So if we wish to use a Gaussian and we want to fit a Gaussian to this real underlying bimodal distribution, then probably what we will learn is something like this, right? And this is because we are trying to represent a bimodal distribution through a unimodal distribution. Does this make sense? Any questions or doubts here?
Is there like scaling component to continuous distribution as well? Dimensionality.
Sorry?
Like for higher dimensional continuous distributions, does it also like not scale?
The continuous distribution? Of course, depending on the distribution that you care about, this might or might not scale well. In general, like say we are just looking at an n-dimensional Gaussian, this is pretty compactly represented by a mean vector and a covariance matrix, which might be much cheaper compared to having a binning in n-dimensional space. Right. Yeah?
Could you also just account for different modes by just adding one mode signal to like the R-squared increase as well?
Yes, exactly. So this is a great segue to the next slide.
I'm not even
So indeed the point is, so these are ways of representing distributions. How can we be more expressive in representing multimodal distributions? One example could be, as you were exactly saying, let's fit a Gaussian mixture model to our data. What is a Gaussian mixture model, or GMM for short, is that we're basically defining, rather than a single unimodal Gaussian, we want to learn the parameters of a mixture of Gaussian distributions, which is usually comprised by k Gaussians. So we will be defining the mean and covariance matrix for each of those k Gaussians, together with a weighting factor, or at least k weighting factors, W1 to WK, which basically define the weighted average of these individual Gaussians. right? So in practice, the Gaussian mixture distributions are quite powerful and expressive, because through Gaussians, we can easily approximate potentially complex functions, right? So we could have, indeed, kind of these three Gaussians being somehow combined through appropriate choice of the weights to maybe measure, to represent a distribution that is extremely non-unimodal, right? A caveat, of course, in Gaussian mixture models is that the choice of k is a hyperparameter and has to be chosen in advance. Again, this is usually something pretty empirical. That is, you just try different numbers of k and see what works best. The trade-offs here could be the usual ones that come with respect to overfitting and underfitting of data. If I have very high k, I might be fitting very well my training data, but this doesn't really generalize to my testing data or inference. Or we could define k based on some domain knowledge, right? So we may know that the policy actually has 3 distinct modes, and so we might just pick that as k. But in general, it's a hyperparameter. A second class of approaches to represent or expressive ways of representing multimodal distributions is what I'm referring to here as the discretized plus autoregressive approach. So we introduced before this idea of discretization to represent multimodal distributions, but we mentioned that scaling this to high-dimensional actions for us, or in general, high-dimensional distributions, could be expensive. Again, I think a nice visualization could be something where, say that we have a 2-dimensional distribution that we wish to estimate. The discretization in this case would essentially be equivalent to picking a discretization in our 2-dimensional space and having to pick a specific value for each of these grid cells. You see how this scales very badly. And specifically, not only does it scale badly in the sense of number of parameters that we want to estimate, it also clearly suffers from the curse of dimensionality when we look at model learning. And this is because in reality, we will only be estimating our distribution from samples from our underlying distribution, right? And so in order to populate all of the grid cells, you see how we would need an exponentially large number of samples from our distribution. So a neat trick is the one of basically decomposing autoregressively this 2-dimensional distribution. What does this mean? In general, we could represent exactly a joint distribution over x1 and x2 as basically the product of the conditional distribution x1 times so the probability of x1 times the probability of x2 given x1. And this is an exact reformulation, right? So we're not losing anything. But what we're gaining is that rather than having to discretize n-dimensional space, we only do 1-dimensional discretizations, right? So in practice, this would mean something like we only need to discretize the 1-dimensional vector. So this would be like p of x1, and this would be p of x2 given x1. And only have to learn these two 1-dimensional discretized representations. And here, not only this is more efficient from the perspective of total parameter count, it is also more efficient with respect to the curse of dimensionality issue that we were describing. Because here, while the samples in this 2D grid are pretty sparse, the same 4 samples would be clearly denser in these 1-dimensional vectors, right? Because we would be using the same 4 samples, something like that. in practice, this is exactly what people do when using transformer models for robot policies. So in this case, you would be your one-step probability distribution would just be the transformer. You would have some context, which could be maybe some camera image, maybe some natural language prompts that describe your task. And you're learning your distribution over next element in that sequence, where this could essentially be, again, let us look at this more visually. So in natural language, in LLMs, you typically have some transformer block that takes an input like a token here, maybe a sequence of those, and basically predicts the next token in that sequence. Right? We can just call it maybe xt. In order to predict this, then you would be autoregressively introducing the predicted xt here, predict xt plus 1, and so forth, kind of doing this autoregressive prediction. Here we would be taking this exact framework. That is, we only learn this one-step prediction rule, where xt, rather than being tokens or words, as you would do in LLMs, here the xt could be one dimension of our action. Right? So if we have an action vector u that is comprised of like a steering angle and an acceleration, we might have this decomposed such that we first predict the steering angle, and then we feed the steering angle back to our model and predict the acceleration. Does that make sense? Yes?
You just have the problem and still has like that dimensionality. You still have to go through and understand everything else before you can run this online and narrow things down.
I would say in terms of dimensionality, no, but here you're basically trading off kind of ease of representation with compute. Because now you would not be sampling all at once, but you're sampling autoregressively. So in order to generate the full vector, which might be n-dimensional, you would have to do n steps, n calls to your, in this case, transformer block. Okay, again, so this is very, very popular in practice. Another class of models, also very popular, especially over the last couple of years, is basically relates with diffusion processes and diffusion models, and even more recently, I would say over the last couple of years, flow matching. And the idea of diffusion in general is that, so we're saying we want to sample from a potentially complex distribution, but obviously we don't know how to sample from this potentially wild distribution. But in general, we might have some easy distribution, say a Gaussian, from which we know exactly how to sample, and this is easy. And so in the diffusion processes in general kind of cast the problem as wanting to transform a sample from a simple distribution which we know how to sample from, and then transform these samples such that they match the target distribution that we care about learning. And so in practice, what diffusion typically defines is a process whereby at sampling time, we would go from noise to the actual realization that we care about. So we want to learn this transformation. Diffusion models were originally introduced for generating images. So I would say nowadays, basically any image generation out there is using some form of diffusion model or a flow matching representation. And the goal here is to map from pure noise, given some conditioning, for example, generate an image of a cat, to the actual image that we care about generating. So the sampling direction is pretty straightforward. We want to take noise. We have a learned kind of transformation, and we use this to gradually and iteratively denoise, going from noise to actual image. The tricky one and interesting is, of course, the backward direction, right? So how do we learn this mapping? In practice, for diffusion models, this is done by learning this individual denoising step. So what you would do is you would take your data set of images and define kind of gradually more noisy versions of those images, right? So we would take like x0 and then define kind of x0 plus some noise, and then define, and this would be x1, and then we define x1 plus some noise, this would be x2, and so we gradually generate more and more noisy versions of this image until we get pure noise. And the goal in diffusion models, we then want to approximate this noise term to basically being able to reverse the process. Right? So at data generation time, we basically have the forward generation where we just add noise to our image. And then we want to approximate this noise through a learned parametric mapping f of theta, which then allows us to go in the reverse direction. Again, I'm aware this is pretty hand-wavy description, but I'm happy to provide references for diffusion models in practice. But the bottom line here is that diffusion models and flow matching models are extremely powerful ways of representing these multimodal distributions. But let us look a little bit more closely into flow matching. And the idea is that if in diffusion models we are interested in learning this error term epsilon, this noise term epsilon, to be able to reverse the kind of the denoising process. In flow matching, what we want to learn essentially is a vector field to do this iterative denoising. So we're basically describing this statistical transport problem, where we want to move samples from a simple noise distribution into samples from a potentially complex distribution. So in practice, at inference, the way this goes is that assume we have learned a vector field, v of theta. At inference, we would be sampling a point x0 from our noise distribution, and then we would kind of generating a data point from our target distribution essentially entails integrating forward this vector field. And we can do this through Euler integration, for example. Again, kind of the caveat here is how do we train and how do we learn this vector field? And at training time, what we would be doing is that we sample a couple. So we would sample a sample x0 from a candidate initial distribution, say a Gaussian. We would sample a point x1 from our data set. That is a sample from the target distribution that we care about learning. We would sample a time step t, usually from a uniform distribution between 0 and 1, because we are assuming that our kind of denoising step goes from time 0 to time 1. And then in flow matching, we basically linearly interpolate between these 2 points. This would essentially mean kind of drawing a straight line from our sample to the target sample from the target distribution. And we basically update the parameters of our learned vector field such as to minimize the distance between our prediction of the velocity, essentially, with the target velocity between those 2 points. Because x1 minus x0 is essentially the target velocity, right? And so in practice, what this would look like is something where we have our easy distribution, say a normal distribution here. We have our complex distribution here. And what we would do is we essentially learn a vector field that kind of guides us from every point into sampling from this distribution. Of course, imagine this vector field to be complete. But then in practice, we would be sampling from our distribution and just integrating forward, for example, through Euler discretization, Euler integration, our samples to generate samples from this other distribution. And I would say flow matching is very popular these days because it's extremely powerful at representing continuous distributions, which are ultimately what we care about in robot control, for example. Any questions here? Okay. A last trick that I wanted to make sure we covered is the one of action chunking. So until now, and throughout this course, we've always been discussing kind of feedback policy in the form of a distribution over next controls given states. And so in general, the framework is something where we observed some state xt, we had some policy from which allows us to basically sample an action in that specific state. We would be executing this action in the environment, and then we would observe a new state and repeat this process. And so visually, this would look like at all time steps from 0 to 7, we would be generating one action, executing that in their respective time steps, and moving forward over time. Action chunking, however, which I would say right now is the most popular way of parameterizing kind of robot learning policies, is something where rather than predicting a single action, we are basically predicting actions over a specific planning horizon of length k. So if you wish, this looks like something like model predictive control, right? So we're basically predicting k actions in the futures and executing those k actions in our environment. So this became pretty popular, first of all, because it tends to work quite well, so people just adopted it. In general, I would say that a clear benefit is that this allows more time for inference. So if we have pre-computed the actions for the next k time steps, then we can just trust our predictions for the next k time steps and only have to recompute new ones after k. Another more subtle motivation for which it is believed that these models perform, and it's been shown that these models perform better, is that in general these leads to smoother control trajectories. So if you look again at what we're doing here, typically our policy pi would be a learned object, so pi of theta, and we would be calling this object essentially at each time step. And since this learned policy might not be perfect, the learning signal might be a little bit jiggery because we are basically introducing some randomness at every call, right? If we, however, predict a full prediction sequence, then kind of within this short horizon sequence, typically the generations are more coherent between each other. And so this leads to smoother controls, which typically are kind of deployed with better performance. But this is definitely another trick of the trade, if you wish, that is worth knowing about. And so some examples. This work, the fusion policy, was pretty popular, probably now dating back 3 or 4 years ago. It was one of the first examples of leveraging kind of the fusion models and the fusion policies at scale. So in general, here we're going from an image representation observation of our state and using the fusion models to generate a full trajectory of behavior for our robotic arm. And it was shown to be able to do extremely challenging tasks, generalize across different conditions. And so the results here were very good and exciting at the time. So not only are we using diffusion models, you'll also notice that here we're using this action chunking idea. So we're generating a full trajectory rather than a single action. And so this is definitely a work that I suggest you go check out. Another example will be the kind of robotics transformer series of works. There have been follow-ups to this work. But at the high level here, I wanted to show the case where, in general, here we're learning a mapping in the form of a transformer model that maps from a history of images. So again, if you think back about our multiple time steps, multiple observations of history, and a language description of the task that we wish to execute, to a discretized representation of our action, where we have been essentially doing this discretization plus autoregressive generation. So here, the arm had different actions that it had to execute, and we were basically, in this work, they basically generated each of these dimensions individually and conditioning on the previous one to do so. So these are just examples of the topics that we have been discussing today. And so, at a high level, I would say that we have been touching these common pitfalls and possible strategies to remedy for these pitfalls that range from algorithms that were targeting those pitfalls. For example, Dagger. We looked at smart data collection and augmentations. Take the 3 cameras and the fictitious augmentations, and we had kind of a big parenthesis on how can we represent the full distribution of our data, because this is ultimately what we care about when learning from demonstrations. And so I would say that we have seen behavior cloning, and kind of a classical benefit and pro of behavior cloning is that at its core, it's essentially supervised learning, right? Plus minus some kind of deltas. And I would say that supervised learning is definitely easy to implement and monitor. We have good metrics. We know it's usually well behaved from the perspective of gradient descent. And so this is usually pretty simple to implement. It's also pretty efficient. So there is no need for trial and error learning, as we will see starting Wednesday in reinforcement learning. And there is no need for an explicit reward signal. So in some cases, defining a reward might be harder than learning to kind of devising a policy itself. Take the case of driving. How do we quantify numerically what good driving is? On the other hand, learning a policy to mimic expert demonstrations of driving is actually much more tractable. On the cons side, of course, kind of all of this assumes that we have a strong dependency on the quality of the demonstrations. So if the demonstrations are bad, then there is no way that the learned policy will be good. Of course, these strategies that we discussed today are ways of addressing kind of the compounding errors problems, but these problems remain. And in general, generalization of learned policies is a big topic. And linked with the first one, in behavior cloning, there is no exploration whatsoever, right? So we will have no way of discovering new solutions for the task that have not been kind of demonstrated from an expert. And so this is where kind of reinforcement learning will come in the picture. Okay, any questions on behavior cloning? Okay, so I want to quickly touch on a couple of, actually one other paradigm for behavior cloning, and then give some pointers to inverse reinforcement learning methods. So one interesting idea is that can we use kind of ideas from behavior cloning to try to approximate the objective of reinforcement learning? That is, can we go beyond or at least filter out the performance of demonstrations in our data set such that we are able to get as close as possible to the best kind of performance that has been shown in the data set and potentially kind of improve on it. And so the idea here is that rather than relying on solely optimal demonstrations for a specific task, we might want to leverage a broader set of demonstrations, for example, from suboptimal policies or related tasks or things of the sort, and slightly shift the learning problem that we are positing in order to get the best from our data. And I would say 2 main classes of methods are the filtering or weighting of demonstrations or devising different conditionings for our policy. So let us go into the details because I think this will be will be clearer. So in general, we have been discussing the idea of behavior cloning completely detached from performance, right? We had no measure of reward that was scoring how good that trajectory was with respect to another. And so a kind of very simple idea is, can we introduce some of these considerations by essentially reintroducing the reward function as a player in this game, whereby we might, for example, a simple idea would just be doing filtering. So say we have a reward function that is able to score a specific action in a how good was an action UT in a specific state. This may allow us to score the quality of entire trajectories, because we could just score, we have a rollout in our data set, we might just be summing up the reward accumulated over this trajectory, and then we could basically filter out our data set such to only keep the trajectories that are better than some value or bar that we fix, right? So here is a very simple example in which we know that there is performance in place. Let us just focus ourselves on the good ones, on the ones that are exceeding some threshold. Another mechanism could be to do weighting. So we have, again, some mechanism of scoring our transitions and trajectories through our reward. So let us modify the learning problem, for example, the maximum likelihood estimation objective, so that it becomes a weighted version of the original objective, where the weights come from the performance itself. Right? So we don't want to mimic all trajectories blindly, so maximize the probability of all trajectories blindly, but what we want to do is maximize the weighted probability, where the weight is essentially the performance. Yes?
Filtering the quote-unquote best trajectories from what we were talking about before, where we want to augment, like purposefully augment the suboptimal trajectories.
Yeah, it's a very good question, and I would say that the answer here is very case dependent. So it'll depend on the application that you're working with. I would say that these filtering techniques are particularly good in the case where you have a very narrow task and where you don't need to collect this corrective behavior. But while here, what you care about is really focusing on, I have these very good trajectories and I want to learn to exploit them. This could also be very good if your dataset quality is just very broad. So maybe I just have trajectories that are extremely bad in here, and maybe my dataset is also extremely large, and so you have no ways of manually annotating what is useful and what is not, and so you devise some simple strategy to filter out bad things. Yeah. So I would say it's parallel axes in devising towards your solution. Yeah. Okay, and another idea is that we might want to enrich the kind of conditioning that we have in our policy. So until now, the policy for us was distribution over controlled given states. But I think two particularly popular approaches are to condition the policy on maybe a candidate goal state for goal conditioned policies, or a candidate performance that we wish we'd have from our model. So something where we might condition it on a candidate total reward for our trajectory. Why are these reformulations useful? And I think this can be easily observed from the goal conditioned one. So say that we have some data set where we have a number of trajectories, say that go from some x1 to some candidate xt. Now maybe from the perspective of the task, this trajectory is very bad, because maybe xt is very different from the actual goal that we had over here. However, this is a good trajectory for showing how we are reaching maybe state xi. Right? So if the goal is not to solve a task, but to reach a state, then every trajectory is a valid trajectory for showing an example of how we are reaching a candidate goal. Right? So in our case, this trajectory here, despite being bad for the task of reaching this goal state, learning from this trajectory as a means of having a general trajectory that could reach any candidate goal, this is actually a good thing to do. Right? So in some way, once we have learned this goal-reaching policy, then the problem becomes, at inference, I want to query my policy to reach a state that is good for me. Right? So I'm basically learning a general mechanism to reach any candidate goal state from my state. And then at test time, I want to condition this policy on reaching a state that is good for me. Right? But in this case, all trajectories are useful with this regard, because all trajectories are good realizations of reaching all the states along that trajectory. Okay, and same thing for reward conditioning. Okay, so just a quick mention on inverse reinforcement learning. More than a mention, I would say pointers for you to dive deeper if you're interested. Remember that in behavior cloning, we wish to estimate the policy that approximates or mimics the behavior of an expert. In inverse reinforcement learning, we care about learning the objective that is being optimized by the expert. And in general, I would say that, so more formally, the goal of reinforcement learning is to recover the reward function, which we think is being optimized by the expert. In practice, this means that we will be often parameterizing a reward by some parameters W. And the goal is to find the values of those parameters that better explain the expert demonstrations. There are a number of inverse reinforcement learning algorithms, as you can imagine, but I would say that at a high level, kind of the skeleton of most of these algorithms is something like the pseudocode here on the slide, whereby we will start from a data set of expert demonstrations, and we will have some initialized reward function parameters W and policy parameters theta. And then most algorithms typically alternate between two separate processes. We'll have a first process whereby we update the reward function parameters according to some objective. And then we will use these newly computed parameters W to optimize for the parameters of the policy. So we will have an estimate of W. We will use this estimate to basically maximize the policy with respect to that objective, and then use this policy to improve the estimate of W. Again, so this is very high-level discussion, but just to let you know that most of these algorithms should be seen from this lens. And kind of popular algorithms are apprenticeship learning, maximum margin planning, and maximum entropy RL. So I would definitely start from those. And these algorithms, kind of to some extent, all try to address the challenge, or one of the key challenges for inverse reinforcement learning, which is the one of reward ambiguity. And this is basically the problem where there could be many reward functions that explain the same data. And so these mechanisms really try to design these two individual processes such that we don't fall in this reward ambiguity. Okay. So just to conclude, we have been introducing, I would say, most of the techniques to basically build a mental model, I would say, of how to deal with imitation learning. We focus most of our narrative on behavior cloning, where kind of the V0, kind of naive formalism of behavior cloning is that we have a data set of expert demonstrations, and we want to learn a mapping that approximates the behaviors in our data. We saw how this naive version is basically prone to suffering from two main challenges: compounding errors and the multimodality of behavior data. And we saw how we could tackle this from a perspective of data collection through smart augmentations, a perspective of algorithms, say Dagger, and expressive models that try to capture the multimodality of the data itself. And then briefly mentioned two alternative formulations, such as reinforcement learning through via supervised learning and inverse RL. Any questions on this? All right, then see you on Wednesday.